Why is social science and political science obsessed with hypothesis testing in recent years? Why should we try to spend the time and effort at trying to make explicit hypotheses and test them using the kind of techniques that we're going to be talking about in a second? And I think there are a couple of different reasons. First, it forces us to think clearly about the links that we have between our theories and the real world implications of our theories. Often, students have a hard time trying to come up with and verbalize or operationalize their hypotheses from their theories. First of all, because it's difficult to make an argument that you feel summarizes the most important elements of the relationships that you're talking about in your research, and how that might be different from what the literature has done previously. Second of all, it makes us try to write down what we think is going to happen when we tutor our theories. What are the implications for it in the real world? Secondly, it forces us to be clear about what our null hypothesis is. For students in my classes who want to try to operationalize them, that's great. You also might want to write the null hypothesis to make it clear about what the alternative is that you're evaluating your main hypothesis against. That the null hypothesis is that there is no relationship between your outcome and your causal factor. Third, I think it forces us to frame our implications in a falsifiable manner. If you have a hypothesis, as economic growth goes up, the likelihood of a country being a democracy goes up. If you find the opposite, that is, economic growth goes up, the likelihood of a democracy decreases or doesn't change, then your evidence, your argument can be proven false, or that the evidence doesn't support it, right? That you have to frame things in a falsifiable manner. And when we do this, and when we conduct hypothesis testing, just from the basic kind of relationships between an outcome and explanatory variable, there's a couple of different ways of doing this, depending on the characteristics of your data. We talked about the different forms of variables, right? You have nominal, ordinal, continuous. Here you can break them up by categorical, which would also kind of fall into kind of like 0, 1, right? Is a bead black or white? And we've seen some of these already. So Pearson's correlation coefficient, when you have two continuous variables, we've seen and we estimated that a couple of weeks ago. Difference of means test, we're going to get to. That's when you have a continuous and a categorical. Tabular or goodness of fit analysis, we're going to do in this section. That's when you have two categorical. Logit and probit, I'm going to mention them at the end of the term. They're outside the scope of this class, but that's when you have a categorical dependent variable, often for the case of logit and probit, a dichotomous variable. You have other ordered logit and stuff if you have categorical variables that have more than one category. But the takeaway from this is that depending on the nature of your data, your independent and dependent variable, you can run different types of tests. What do these tests have in common? First, they use probability p-values, probabilities in their hypothesis tests. These p-values can range from 0. They have to range from 0 to 1. They represent the probability that the relationship we find is due to random chance. And they include the null hypothesis, that if it isn't, if it's above a certain threshold, then you fail to reject the null. If it is above that certain threshold, evidence supports the alternative hypothesis. Several other things that they have in common that they do not tell us. First, they don't tell that the relationship is causal. All we can do, unless you have an experimental analysis that we talked about earlier, is that there is correlational relationship between these two variables. All these tests don't tell us how strong the relationship is. They'll tell us if the relationship is different than 0, but it won't tell how steep that curve is between the two relations. They also don't tell us anything about the quality of the data that we're using, connecting to the earlier point about garbage in, garbage out. The first method we've already covered is the Pearson's correlation coefficient. And we see here, in which you can see we're looking at derivations for values that use that I value there minus the average values of either X or Y, and we calculated all that by hand in Excel. Ordinary least squares regression we're going to get to in a second. You also have X's and Y's, but then you also have that estimated relationship between X and Y is that beta, and the alpha there is the value of Y when X equals to 0. We're going to get back to that in a bit later. The important thing also with regression analysis is the ceteris paribus assumption, is that all other things being equal, that if you have this equation, anything that you don't include in that equation is either part of the systematic error or the random error. The systematic would be things that are affecting the outcome but that you don't include in your model, and then just the random noise is that random error. Okay, so I thought I would go ahead and use an example related to the recent election here in Canberra, using the goodness of fit example, that tabular analysis. I chose the two candidates in the Canberra electorate in the federal election for the Greens, Tim Hollow and Alicia Payne. And I was really interested in the differences between the first preferences in-person voting versus postal voting. You see the difference in percentages. Tim Hollow received 25% of the in-person first preferences and only 20%, about 21% of the postal percentage of votes, while Alicia Payne received 45% of the in-person percentage of votes and 44% of the postal. So you can see the total number of voters by either in-person or postal in that bottom row, and the average percentage of people, the average percentage of the vote across these two for Tim and for Alicia, almost 23% for Tim Hollow and almost 45% for Alicia Payne. However, because there are other candidates, these probabilities don't sum up to 100. Of course, if you included all of them in that larger table, they would sum to 100. I have a main hypothesis that these vote totals are not independent for how people voted, whether in person or postal votes. The null hypothesis is that candidate vote totals are independent of how people voted. There is no significant difference between those that voted in person versus via post, right? So this is kind of an early hypothesis test back in the days in which computing power was hard to have, and it was hard to run multiple regression just kind of practically, and so you would just kind of look at these kind of tabular tests. So you first want to look at just kind of expectations for if there is no relationship between how these people voted. That would be that null hypothesis, that the percentages that both the candidates would get would be the same regardless of whether they were in person or postal, taking that value from the end of the row. And then you can say the expected cell values if the vote choices were unrelated. So you have the 22.93% of the bottom, the total votes by type. That would give you the expected value for Tim Hollow, for example, for the Greens of 12,339 votes for in-person. Postal values would be 1,482. So I'm going kind of quickly through this because this is not a frequent kind of analysis that people use in modern political science, but I think it's important to kind of highlight how you can kind of use these kind of hypothesis tests to a whole bunch of different kinds of data that you use. And so you see here the expected versus the observed values. So Tim Hollow received more in-person values than expected at 19,240 compared to 12,339. You can see the others for the other different cells. And I did all this in an Excel spreadsheet. You can do it in Word. You can do it in statistical softwares. But what we do is try to see whether the difference between the expected and the observed values are statistically significant. And for here, we're using Carl Pearson's chi-squared test, in which you look at the chi-squared distribution, and you do the chi-squared statistic is just the sum of the difference between the observed values and the expected values. You see, hopefully here, the parallels with the correlation coefficient when we're looking at the difference between the observed values and the expected values over the expected value for each one of those 4 cells. I calculated these values, broke them down, and the sum was 13,312. And with all of these statistics, you have to look at the degrees of freedom. When basically the degrees of freedom are important because you need to have. So if you're trying to look at like a relationship between an x and y, and you only have one dot, you can't really decide whether there is a fundamental relationship because you can't really draw a line. You can run an infinite number of lines through that dot, and so you have no real you don't have enough information to really make a conclusion. If you have 2 lines, then you could draw one line, but then you're not really sure if that's the particular line because you have those 2 dots of information. So you can have one statistic, but you can't calculate the standard deviation around that statistic. So for the chi-squared statistic, the degrees of freedom is given by the number of rows minus 1 times the number of cells minus 1. So here we only have 1 degree of freedom, so you can only calculate one statistic. So then we go to your handy dandy. Well, I guess you can go to Google, or you can go to a statistics textbook that often have these critical values for these different distributions. The Appendix A for this for the Kelstead and Witten book, they include the chi-squared. Then you have the t-statistic, which we talked about a couple of weeks ago, and you can see that the critical value for chi-squared with 1 degree of freedom at the 0.05 level is 3.841. If you go up to the 0.1 level of significance, again having more room in the tails of that standard normal distribution for the t-statistic, you see the chi-square statistic goes down. So as you get more demanding for your level of significance. So for a 0.01 level, the chi-square statistic is 6.6. But for here, the number is dramatically higher because we have such a large number of people in our sample. The value is higher than the critical level, so we can make that overall judgment that this is a statistically significant difference depending on the type of voting behavior, and we reject the null in this case. And you can also just generate the chi-squared statistic in Excel using that command that I show here. So this is one way of conducting a hypothesis test. We're going to do another one in a second. A couple of important takeaways here. First, there's different types of tests for different types of data and hypotheses that come with them. They all form some form of significance test. Here, the distribution was distributed in a chi-squared, not normal distribution. Chi-squared, as it gets higher numbers of degrees of freedom of observations, kind of approximates the standard normal distribution. These statistical tests rely on probabilities that are related to the distribution of the sample means. Here we saw the row means and the for the different options here. But the sample means, right? The repeated draws from these from the samples that we have. In this example here, it was voters. But for any of these examples, you're just taking these repeated draws, and each one of these draws has a mean value, and you take a number of them. They're going to be normally distributed, and you can derive statistical significance given the standard normal curve. With that, I keep repeating it, but I think repetition is helpful in trying to understand the connections that we're looking at, observations, derivations from the average value, the expected value, and statistical significance of these different statistics to see whether our results are due to chance or potentially the correlation that we're interested in finding in our data connecting to our theory. With that, the next question we're going to ask is why we should run a regression. An excellent question to ask.